everywhere.
I think I got somebody's notes up here. Nah, man, they're mine now.
Yeah, you have 10 minutes. Johnny, for 10 minutes, then you can. It's over Zoom, right? You don't have to travel. Yeah, please, you can watch for 15 minutes, then you can leave. Okay? Yeah, let me disable this one. Yeah, go ahead.
Alrighty. Hello, everybody. My name is Kendall Golden. I'm a third-year PhD student here at Georgia State. I am in the Department of Mathematics and Statistics. The reason why I'm in this class is my concentration is bioinformatics. And today I plan on talking about the Oxford Nanopore Technologies Basecalling algorithms. And let's get into it.
Click on the slide and then.
Okay. Cool. Okay. So before I can talk about the how, I have to talk about the what, right? So what is nanopore DNA sequencing, right? So I want you to imagine that this DNA strand right here is only, well, half. Imagine it's cut in half and we have a 1D read sequence. What we have here is a membrane that has a potential, right? And then as the DNA strand comes through the nanopore, it disrupts that potential, and what we have is some signal, some noisy signal. Well, that is our, well, sequence. Or as it's called in the literature, we have a squiggle. Well, this is the what, okay? But moving forward, we always begin with the why. Okay, I talk about the what, the why, and then I'll get into the how. Okay, why? Why use nanopore sequencing technology? Well, first of all, unlike short read sequences, with these long reads, actually super long reads, sometimes 100,000 or even 1,000,000 bases long, we can detect structural differences like large deletions or how do we say, or large structural variations, right? Not only that, but with Minion, which is a somewhat newer, well, pretty much all of bioinformatics is relatively new. Minion is something that's small enough to fit into a backpack, and you can do all of your sequencing on this. That's why you would use it. But why do we need these base callers? Because this talk is about base calling. Well, this squiggle, as you can see in the last slide, I got this from ChatGPT, by the way. I apologize. I know I'm not supposed to use ChatGPT, but I did. This squiggle, right, has a low signal to noise ratio. What does that mean? It means that I cannot look at this signal with any sort of accuracy to determine exactly what bases I'm looking at. Well, not only that, these base callers that take this noisy signal and returns these, well, bases from this somewhat noisy signal are still improving, right? Well, why? Because as time moves on, and like I said, Minion is somewhat of a small portable platform. If you're in the field working with sequencing, you don't want something that's going to take hours, days, or weeks, months. You want speed and efficiency. You want to be able to do it on this Minion device that you can fit in your backpack, that you can fit right next to your laptop, and you should be able to sequence off of your laptop, right? And not only that, but this squiggle may contain additional information besides just that of the bases. Well, how do we do it? How? Well, initially, these base callers used hidden Markov models where you have some probability matrix that determines the change of state right? You can see here that, for example, this black line would be a step transition. You can see that GGT, right, moved to the front and we added an A, right? So you have a single step transition, which is a probability matrix that has weights that decide, well, how probable you are from going from here to here to here to here to here to here. So you have some weighted probability matrix that is the dimension of your, well, not exactly dimension of your K-mer, but if you add up all these lines, that'll give you more or less the amount of cells in your probability matrix. Well, this is all good and well, but we're just getting started here. So of course there's going to be issues with this algorithm because this is the first generation of base callers. Well, the thing is that hidden Markov models have been used to solve inverse problems. What is an inverse problem? Well, we have a noisy signal, that being your squiggle. What we seek is to determine the parameters or the bases that, well, cause that signal. Well, here we can see that it's been used in dynamical systems. Pretty much it's the traditional means of solving a inverse problem like this, where we take the data and we try to get the model, as opposed to having the model, you get the data. Well, the problems, hidden Markov models, well, they have their advantages and their disadvantages. Like I said, this is the first generation. That already assumes that we're going to have additional generations. Well, hidden Markov models are cool because it's well published. I mean, the dynamical systems, they've been using it since, well, 1999 at least. Well, you don't need a large amount of training data because you have to train the model, of course, but it's a small amount compared to, well, later approaches. What's the problem? The problem is built in with the hidden Markov matrices, in a sense. Well, that's exactly the issue. It's the Markov property. The Markov property assumes that the current or the next state is only dependent upon your current state. So it is memoryless. So there is no, how do I say, codependence between the past and the present, right? There is only the present, and how do we move forward from the present? Well, and also an issue with this is you have to train off of a small amount of data. So as data becomes more and more complex, your model as a result becomes less accurate. Well, there's got to be a better way. I don't know if you can see this, but these are like the old infomercials, right? Where this guy's sitting down with his popcorn tray table, falls. This girl's trying to, I believe, cut a piece of bread with a doorstop. And it's a little hard to get here, but she's fumbling to get something out of a cabinet. Well, that brings us to, well, our timeline. You can see here that these are my hidden Markov model base callers. Well, as you can see, that in general, for the hidden Markov model, we have a general increase in accuracy as we progress through time. As we progress, we get more and more accurate. But you should notice the color of the dots here, right? Most of the dark dots are down here. Most of the lighter dots are up here. What does that mean? Well, we have 1D strands and we have 2D strands, right? If we go back to the start, we can see that this would be considered a 2D, well, sequence, right? Because we have both strands passing through. And traditionally, with a hidden Markov model, if you have a single strand, you have much less accuracy. And so, but for the 2D, you can see that we do have accuracy. Okay, it works well, good. But what I want you to notice is that as we progress from hidden Markov models to recurrent neural networks, we have a large spike in accuracy. But not only that, but we have, most of these dots have become shaded in. So what does that tell us? It means that we have accuracy from only reading one of the strands, which from a chemical standpoint, I don't really understand the complexities of it. But from a chemical standpoint, I know that it is easier to work with a 1D read. But you can see over time, base callers not only progressed past the hidden Markov model, we have recurrent neural networks. I'm not sure exactly what transducer is, but my basic point here is that we moved beyond the hidden Markov model, and we are now upon the recurrent neural networks where we can have much greater simplicity by only having 1D reads or sequencing. Well, how is it done now? Okay, this is, well, a timeline that, well, stops, right? We have 16 all the way to 17. I think this ends somewhere at 2018. We're in 2025. What's going on now? Boom, Rubicon. This is a framework for optimized machine learning base calling. How does it work? Well, as we have a nice little diagram that I stole right off the paper that we can see we have Quabus, I call it Quabus. Quabus is quantization aware base calling architecture. What is that? Well, it's a search. It's a search that you perform on base calling architecture to find that which is optimized for your hardware and the sort of data that you're about to deal with. So, in a sense, you perform this Quabus, which is admittedly computationally expensive, but from there, you take this model, you cut out all the skip connections in your recurrent neural network, which, well, why? Why do you skip clip? Well, these skip connections actually increase the computational load on your hardware. So by cutting out these skip connections, we can improve efficiency, but it is also shown in the literature that you can now train this model after skip clipping it to be as accurate as the original parent model, but still maintaining the increase in efficiency. Well, and then after that, we have pruning, which is when we cut all of the, more or less, the unimportant connections from our network. We cut all of the unimportant connections, which eliminates our parameter space or reduces it by, I believe in the literature, it said maybe about 80%. So Quabus, skip clip, pruning, and then, well, we just train with the proprietary ONT base calling pipeline. And that's how Rubicon works. That's the framework. Well, what are the results? Well, as you can see here, that generally, if we look at the far right-hand panel, which is kind of the average, our Rubicon FP and Rubicon MP is on par, if not greater, than all other base callers in terms of accuracy, right? What's the most important factor? Accuracy. But if we look down here, we can see that even in terms of throughput, Rubicon is exceeding that of, well, the competitors.
Where's the FP?
Oh, I know that. Oh, floating point precision. Maybe if you read the slides on your own paper, you know, you don't have to ask questions. Okay, all right. Okay, all right. Well, what's the good and the bad? Well, Rubicon is cool, right? But there's always trade-offs. There's always trade-offs when we're talking about a new, well, architecture, model, anything. We will always have trade-offs. Well, in general, Rubicon has a large throughput capacity and is modular. Because of this Quabus step, you are able to apply many different architectures to this Rubicon. And from there, you can still maintain the same advantages, but you can use different models for it. Well, of course, these are the good, this is the good, but what about the bad? Well, generally, you have an initial overhead during this Quabus step. It's good because it's modular, but it's also bad because it takes time. This is, well, in a sense, I like to call it, you give a man a hammer, everything starts to look like a nail. You give a man machine learning techniques, he's going to try to apply it to everything, right? So you have taken the machine learning algorithm, we say, we can use machine learning to determine my machine learning algorithm. Well, besides that, right, we also need quality training data for our algorithm. Well, those are my advantages, disadvantages, but I want to move forward. I want to move forward and talk about what's going to happen in the future, right? Generally, I reviewed another paper which gets into more of the future of what we can do with Basecalling. From this squiggle, there is a paper that asserts that more or less we can detect more than just the bases from the DNA RNA sequence. We can determine things like modifications like methylation, right? And then also predict poly A tail length. I'm not going to act like I know what any of those mean, but we can detect them, right? Multitask neural models, right? We can also take this information and feed it back into our network to better train it and better understand this information. And then not only that, we can use this data as further beyond. As these insights become more and more apparent and relevant, we can see this data as a signal. This squiggle, that which I more or less wrote off as a noisy signal, we can see it as something as, well, more than that. And we can draw perhaps deeper biological conclusions and, well, reveal novel insights. That's all I got. That's my references.
Question. Must be a lot of questions. Right, I can start. Can you go back to, I think, second slide? Yes, over here. So each node would be a remarkable model. Why do we have multiple data? Why not just single? Because this is the goal of Basecalling, right? That what is the kind of character that we are reading?
Well, in a sense, how do you train that? How would we determine more or less from a single base what's the next one? I would say that if you're only looking at a single base, it would be very hard to train a model off of legitimate data.
Why is that?
Well, you would have what? How many chains would I have in this model? I would have, my chain would be a 2x2. So how do I train a 2x2 matrix? I think that you need something. This is just speculation. I think you need something with a bit more, how do I say, richer dynamics than just a single base.
Excellent. What else? You mentioned something about the signal itself.
Yes.
The value of the signal, the amplitude. What happens as we progress in time?
As we progress in time, the signal can actually shift. Well, the signal is not only noisy, but the signal can more or less shift. And then even though you're still seeing the same bases, the electrical signal can deviate from, well, what you understood to be the
That's
correct.
why we need frame reading rather than single. bunch of readings, represent several characters, and then we use those to monitor how the signal behaves. That's the second thing. Third reason, what could be? So it's related about the technology itself, about the equipment. So if you go back to your ChatGPT, yeah. So over here, when the DNA strand, single strand, slide in the hole. Now there is a reader, physical reader, that read the electrical signal, the squiggle itself. Right? That reader cannot read at the scale of single bit. Just let the DNA slip in, then you have no control to control only single base movement. Due to gravity, the DNA just slip in. You cannot control the amount of DNA that passes through the electrical.
Yeah, it's a variable speed.
So the
Yeah.
reader itself is really huge. The head of the reader itself not read single base effect. It will take a bunch of effects that corresponds to a bunch of characters rather than single character passing. And even recently, they start to double that reader. Have two readers next to each other. One of them will be reading the first few characters. The next reader will read the next few characters.
Is that the duplex?
No, duplex is something else. Duplex is rather than reading from the first character, which is T, and then G, and then G. After you finish reading everything, you flip back the head, which is the T in this case, and you start sequencing from the T again.
Oh, back.
So
okay.
instead of doing T, G, G, C, G, now you go back again, you start G, C, G, G, T. That's duplex because you are base calling twice from both directions. But you can call this duplex reader or something like that, or double reader, because you have two heads and they're reading.
Exactly, yeah.
That's why you have each reading, the squiggle, the point, any point. Squiggle is not a fact of single character. That's why it's really hard to figure out what kind of basis. But that was nice reasoning. So, do we have more questions? Just come up with them. Very interesting.
The Ruby card you use, is it like a thing or who
It's a framework.
you tried it out?
I looked at the data set. It was like 20 gigabytes. I don't have that much space on my computer.
About base caller from ONT.
The Nanocall?
Nanocall is very old.
Yeah.
Any of the most recent
Stay tuned.
ones. In one day?
One day.
Okay. Yeah, I think straightforward, right? Don't need to train. You already have trained content, download.
Okay, gotcha. Okay.
There are lightweight version of it. That as well. The comprehensive version. It's Weber. That's the powerful. So we don't have limitation. It don't require you to run specific tool and be very comprehensive and challenging tool. Just want to get you familiar with these tools without the potential problem. Sometimes you don't figure out what is the problem with my own tool until someone else third party investigate what's happening. For example, if I ask you to publish a tool as part of your paper, then you will just initiate a repo in GitHub, right? You put the source code there, done. What is the README? What is the instruction to run? What I expect after I run? Am I doing it correctly? What are dependencies? Should I install before, right? And sometimes we require you to have TOEI data, some small data set rather than real data set, and also upload that on GitHub. Why is that? Because they want to educate people. My tool got the data set, test the tool works fine. So I tell them this is the data and this is what we do. So getting all those like in practice feel nice example, nice I would say practical example how you should build your own going back to the next. What is it actually?
The-
Floating point and the. Is it precision for what?
I'm gonna go out on a limb here and say that it's the precision of the electrical signal.
It's related to that, but not really. Can you go back to hidden marker model? Yeah. So what do you do? What are the weights?
The weights are trained. So, is that the amount of training?
No, it's the precision of the weight itself. Data.
Oh,
For example, I'm requiring floating point 7, 8, 2. That will dictate the size of the number, how much it can grow. Right? That weight be like thousands, a million. What is the size? This is the limit. Now, if we make it very small, 2 bits, for the weight, can go from 0 to 3, 4 values. I go with 3 bits, I go to 8.
yeah,
4 bits and so on can grow. But this comes with the cost computationally.
yeah, exactly.
These weights need to be held somewhere for storage and process, which take more instructions, longer number. So there are a lot of research. This is relevant even to any machine learning. You want to make it faster, you reduce it with precision itself. 2 bits and 1 bit and 32. So that affects the accuracy right away.
I see.
Makes everything faster, but the accuracy would be better. And mixed precision means did I use floating point or fixed point? Did I use like integer number or fraction? Right? So with fraction, I could have fine-tuned detail. Fixed point, I lose this. Now, neither this or that is good. Best thing is to have mixed.
I
So one
see.
layer might be floating point, the other layer number.
I see. And then, so I guess that begs the question, because if I look at the throughput figure here, more or less, why is the floating point? Well, pretty much. I mean, it's almost half of the throughput.
That's an excellent question. If you look in the accuracy, it's almost the same.
Exactly.
Looks like so it really depends on what parameter you use. For example, if you choose fixed point, how many bits?
I see.
How about the floating point? Also 16 or 8 bits, 2 bits, 4 bits. So we need to look in those numbers to understand what's happening. That is a very nice question. And example, rather fast, faster than floating point.
Yes. The accuracy. Something.
This is worse. Yeah, we need to look into the number. So that decision, you can see the trade-off.
Yeah.
Want to go with faster or higher accuracy? Can you combine both of them? The answer is simply not, because even if you change the data set, 12.2 slightly, you can see this clearly. For example, what we call mixed precision over different point in the x-axis. Sometimes it exceeds the 10,000, sometimes below the 10,000 kilobases per second. And that is for different genomes. Even if you change the data, performance is expected. Although it's slightly different, it's floating point, there is drastic
Yeah.
jumping between hundreds of thousands. The orange column, second column.
Exactly.
Right.
Yeah.
So that is also should be taken into consideration. Data will play a role here. Data, the number of bits you choose for the precision also will affect this trade-off with accuracy. This is very important.
Gotcha.
That's why it's a framework. It's not a single way to do it. So if you change the data, might be more active skip clip, might be more active as a layers, as a node, and so on. So you cannot prune them.
Oh, I see.
So
Yeah.
it really depends on what you are utilizing out of this model. Most of the time, a lot of nodes are idle, not used, not utilized at all. We can skip them
Yeah.
without affecting them. But if we change the data and then something happens, idle state, we cannot prune them without affecting.
I see. So
That's why it's a method on how you optimize any model.
Yeah.
Whatever the architecture.
I see. Well, then I guess it's interesting, an interesting question to kind of ask. How do you go through these two steps without first training?
Excellent, excellent point. There is a way. On machine learning, it's very well known. You mentioned where you run as a first pass to the entire model.
The parent.
You run for any data, and you train inference. You do the inference and watch those nodes.
The
Which
teacher.
one were active? Which one the weights would get changed? Which one were not? You do this not one time, not two times. You do this like thousands of times. Then every time you observe what kind of nodes. So you came to know over this by time. Over time,
Gotcha.
you know exactly what you.
I see.
But for training here, what we meant by training is traditional training. Like now I've already pruned the network. I want to train it.
Oh,
Then do
okay. Yeah.
inference. This is not related to pruning.
Yeah.
But as part of the pruning, you need to do the training and watch the model.
Yeah. Yeah. It's kind of a precursor step. I got you.
All right? Yeah, make sure you run one of these. Have
Bonito.
Dorado, Rubicon, if you want. There
Okay.
are many variations. There is also one for Google. Very lightweight for small devices. So you can try any of those.
Okay.
But I would recommend the Nanopore one.
Nanopore one. Okay.
Dorado or
Dorado. Gotcha. Okay.
All right. Thank you so much.